and we'll be ready to start here, hopefully on time. And send it in. We'll put it in the WCF Experimenter. This is our quarterly section newsletter. Some of our presentations, as a matter of fact, we're going to put in there in the coming issues this year. So for those that missed it. All right. Okay, I believe we are now live. So now we're going to have introduction to the GNU Radio, something you may have heard about, but have no idea what it's about, or maybe just a little bit. So I'm going to turn it over to Tom. Tom, you go ahead and start up your desktop, and I'm going to mute everyone else. And oops, mine just went to full screen by accident. And you may take it away.
All right. Thank you very much, Daryl. I appreciate it, and I hope everyone's having a good conference. This talk is, well, let's go to the first slide, about GNU Radio. And you may have heard of GNU Radio, you may not. It's a free software package. We'll talk about what is GNU Radio, where do I get it, where are the tutorials, some core concepts about GNU Radio, and then kind of the things that it can be used for: simulation, test equipment, and, well, of course, the radio. Everyone wants to listen to their radio. So what is GNU Radio? GNU Radio is a free open source software package. It has both a graphical user interface and a command line, and it's available for Linux, Windows, and Mac. And what GNU Radio does, it allows you to create and run digital signal processing without writing any software. So if you want to learn the basics of DSP, you can go a long ways in that learning without having to purchase anything and without ever having to write any code. One of the really neat things about GNU Radio is it includes a lot of virtual instrumentation. It has built into it an oscilloscope, spectrum analyzer, waterfall plots, a constellation plotter. You can have sources and sinks, and those sources and sinks can be radios, actual radios that source samples into your GNU Radio flow graph. They can come from a file, they can come from TCP IP sockets, they can come from pipes on a Linux system. So you can get input from a lot of different places, you can process it, and you can send it out to a lot of different places. One of the nice things about GNU Radio is that users can create add-ons to the package. So there's a lot of GUI widgets and very specialized functions that you can add into GNU Radio if you have a particular interest in some facet that you haven't seen or you may want to experiment with. So there's a lot of pieces that'll plug in, and virtually all of those are free as well. So you have a lot of pieces and a big toolkit that enable you to do things. GNU Radio supports a long list of radios, and initially, the initial support were the EDIS USRP series radios. Those are all supported, and a lot of folks are using those. I have an EDIS radio, and it's very, very powerful. With my EDIS radio, I build a spectrum analyzer for microwave, a spectrum analyzer for HF, and for other things. It supports OpenHP SDR and the Red Pitaya, if you've heard of those radios. It supports the Pluto, which is the analog devices radio, and there's a huge list of other radios supported. So this is just a tiny short list. There's dozens and dozens of radios. So if you have one laying around your shack, there's a good chance it's supported in GNU Radio. GNU Radio is based on two programming languages, Python and C++. You don't really need to know either one of these in order to use it, and I'll show you that in just a minute here. Python is used for interconnecting blocks, for wiring up blocks, for displaying the graphics on your screen, for letting your virtual instruments have widgets and sliders and things, and for managing the flows. All of the high-speed processing is done in C++. So all the digital signal processing modules, all the buffers, all the file and radio I/O is done in C++. And you don't really need to know how to do that because it's all under the covers and built into GNU Radio. So this is a good slide that John Petrich, W7FU, put together. The first link shows you how to install GNU Radio. And there's a section for Mac, a section for Linux, and a section for Windows. There's some guided tutorials. This links a YouTube video at the novice level you may want to go get. And these links should be clickable in the PDF, so you can download the PDF from the program and then just go ahead and click the links. And then there's some more advanced tutorials on the GNU Radio Wiki. So let's talk about a GNU Radio flow graph. A flow graph is kind of like a program. You don't need to know Python or C++ in order to build a flow graph. GNU Radio Companion, GRC, is the graphical GUI. And so it allows you to create flow graphs, modules, parameters, wire them all up just by using your mouse to point and click between the blocks. And then you click another button and it'll compile your flow graph into a Python program and save that program to disk. And it also allows you to start and to stop your flow graph. So you have kind of a complete development environment, but you don't have to write any code. A flow graph is a Python program. It's automatically generated by the GUI, and it's a text file. It contains the Python source code, and that defines all of the DSP blocks, all of the GUI blocks, radios, sources, and sinks, defines all the parameter values, how everything's all wired up, and how your flow graph should display all of its instruments on your computer. All of that's in that text file. The nice thing is you can save that file and go back to it and run it later if you want from a command line, or you can run it from the GUI, or you can go edit it. You can do all kinds of things with that text file if you want, but you don't have to do anything. You can do it all in the GUI as well. So this is an example of a flow graph. This is a 2-meter narrowband FM receiver, and it comes from the GNU Radio Wiki using a FunCube dongle. And a FunCube dongle is a simple receiver. And this block, I don't know if my mouse shows up here, but this block on the left here is the radio itself. And so you plug in the radio, and then you you define a low pass filter. In this case, the filter is 6 kilohertz wide. So that'll go from 6 kilohertz below the channel to 6 kilohertz above the channel. So 12 kilohertz width with 2 kilohertz slopes. You run that into a squelch. You run that into an FM discriminator. It's called a narrowband FM receive. It's actually a quadrature demod. You go into a volume control and then the audio card on your computer. And you notice these other blocks like options. This will tell you what the options are. You can give it a title. We have a variable called sample rate, which is set at 192,000 samples per second. And that's the rate that the samples come out of the FunCube dongle and go through the rest of the flow graph. There's a range GUI, which is a slider, and it's labeled squelch, and it connects to this variable squelch level, which the blocks is connected to. So when you slide that back and forth, you basically change the squelch level on your receiver. And then there's another slider here, which puts out a number, and this multiply by constant block multiplies the samples coming in by the value of the slider. So it's a volume control. So we have here in this receiver a complete narrowband receiver, and it's tunable. So we have this GUI over here on the bottom left called tuning, and it's input to the receiver. So as you slide that slider around, the receiver changes frequency. Also, there's a waterfall sync here. And so in this case, we can look at the wideband output of the receiver and look at it in a waterfall. And then our low pass filter here lets us just zoom in on that portion of the spectrum that we might want. So that's an example of a flow graph. You draw it just like that in GNU Radio Companion, click the compile button, and then click the run button, and you have your receiver up and running. It's really that simple. So core concepts. A source is something that streams samples into your flow graph. On the previous slide, that source was a FunCube dongle radio, but it could also be an audio sound card. It could be a file. It could be a TCP connection. There's a whole ton of things that can be sources into your flow graph. It doesn't just have to be a radio. A sink is something that removes samples from your flow graph. Our radio. So if you have a radio that's a transmitter, your transmitter is a sink because samples from the flow graph feed your transmitter, and that causes the transmitter to emit RF and go out on the air. You can also sync things into an audio sound card or a file, just the same thing as a source. So in general, a block in GNU Radio receives samples. It does some transformation on them. It might multiply them to make them bigger, or it might filter them, or it might squelch them. It can do all kinds of things to the samples, and then outputs modified samples. So some general blocks, for example, the low-pass filter, the FM demodulator, you can build a delay block in GNU Radio. There's a lot of interesting things you can do. GNU Radio does all the real-time stuff for you behind the scenes. So you don't need to know anything about buffering and buffer sizes and packets. All that's hidden from you. You cannot build a loop into a flow graph. That's one restriction. A flow graph can, if you don't have any real sources of samples, no real sources, no real sinks, then you're basically in simulation only mode, where you can take a signal generator, which is strictly mathematical, do things on the outputs from that signal generator, and then plug them into a virtual instrument and see what you get. So that's great for learning DSP. You can also hook up real radios, real files, and then your flow graph is actually operating on actual real-time data, and you have a real radio. So it's more than just simulation. And there's one other block we'll mention because you'll see it here called a throttle. And if you don't have any source of physical timing, then you need a throttle. What are sources of physical timing? Any real device, like a radio or a sound card, something on it that actually paces the flow of samples in and out. We won't go into more in that. If you're interested in more details, there's an appendix at the end of the slides, and the appendix will give you a little bit more information. So this is the main GNU Radio companion window. This is the one from Windows. The one from Linux looks just slightly different, but close enough that you would recognize it. And like any GUI, there's a new button. And when you do that, you can start a new flow graph from scratch. There's a folder so you can open an existing flow graph. There's a little floppy disk symbol. You can save your current flow graph. You have a compile button. You've got a run button. Those are pretty obvious. Compile will generate that text file. Run will then actually run it. And then you've got a magnifying glass up there for searching for blocks. And you can see over here on the right side of the screen, that's a partial list of blocks, and each of those triangles, when clicked, will point down and open up all of the blocks inside that higher level category of blocks. So there are hundreds and hundreds of different kinds of blocks in GNU Radio. At the bottom left is the console. I find that very handy in that the console, the blocks in GNU Radio can stream debug output or other user information to the console. And for example, tell you if you have something set up wrong, or provide other information that's useful. So let's do the first demo here. In the first demo, we're just going to do some simulation of signals and instrumentation. We're going to use the GUI to create a new flow graph, to wire up the instruments, and to run it. And we're going to do this with what's called a real data type. Real meaning the real numbers, like 1.3 is a real number, or -6 is a real number. So let's go up to the folder here, and you can see I've already, in order to make the presentation go here, I've already started. I have a signal source, which is this block. And this signal source, we tell it the sample rate is a variable name, and GNU Radio always defines the variable samp_rate for you, and it defaults it to 32 kilosamples per second, but you can change that. It's going to put out a cosine wave, and the frequency is 1000 hertz. Its amplitude is 1. And we have a frequency sink here. You'd call that a spectrum analyzer. And that frequency sink uses a FFT size of 1024 samples to display it. and it also runs at sample rate. So we've wired, so for example, if I select the arrow and hit delete, it's gone. If I click the out in the end, I've wired it back up again. So let's hit run and let's see what we get from this. So now we're running this, and as we see, here's our sine wave, but on a spectrum analyzer, a sine wave is just a single frequency. So we see a 1 kilohertz sine wave, and if I move my mouse around, you can see it's right at 1 kilohertz. And the scale at the bottom goes from 0 up to half of the sample rate. So the sample rate here is 32 kilosamples per second. So you can display anything up to and below 16 kilohertz. That's half the sample rate. Interestingly, you'll notice that we actually have 2 spikes here. The other spike is at negative 1 kilohertz. And the reason for that is a real number cannot distinguish a positive frequency from a negative frequency. Anytime you have a real number, you get an image, a mirror image. So anything that's on positive side is mirror imaged on the negative side. So let's go stop that and open up the next flow graph. And here we've modified the flow graph a little bit. We've added a second signal source, and we multiplied the first signal source by the second signal source. So on the spectrum analyzer, we're going to look at the first source here on the top input. We're going to look at the second source on the second input. And we're going to look at what happens when we multiply the first oscillator by the second oscillator. And we'll display that on the third channel of the spectrum analyzer. So when we click that, here's what we get. Let's zoom in on this here a little bit. We'll drag the mouse and zoom it in here. And so what do we see? We see on the first channel, the blue line here, that's the 1 kilohertz signal source. And again, because we're using real numbers, we also see minus 1 kilohertz. The second one was at 700 hertz. That's the red spectrum here. And again, we also see it at minus 700. And then the green pips are the product of multiplying this carrier by that carrier. And what you see are the sum and the difference components. So the sum here is at 1700 hertz, 1000 plus 700. And the difference here is at 300 hertz, which is the difference between those two carriers. So here we can see that a real multiplier produces sum and difference components. It's nothing to do with nonlinearities or anything like that. It's just the mathematics of multiplying two numbers. And again, we also see the negative of the outputs, because with real numbers, we have no way to differentiate negative frequencies from positive. So here we see two carriers and we get the sum and the difference components. So you can play with all of these, change the frequencies, put all different kinds of things in there. So now let's go back to the slides here. And let's talk a little bit more about a couple of things in GNU Radio. In GNU Radio, you noticed on those previous blocks that they were orange I/O pins. In GNU Radio, the I/O pins on blocks are color-coded. So orange means single precision 32-bit floating point number. And if it's blue, it's a complex single precision 32-bit floating point number, which means 32-bit floating I plus 32-bit floating Q. So GNU Radio on one wire will let you wire up a complex number, and internally it does all the bookkeeping for you. You don't have to figure out which part's real and which part's quadrature or imaginary. It'll do all that for you. You just wire up a complex signal. And there's a whole bunch of other types. There's shorts and there's vectors. There's all kinds of things. GNU Radio will only allow you to wire two pins together if they're the same type. For example, it doesn't make any sense to wire a pin that's real to one that's complex. You can select the block, and most blocks have automatically built in different versions that will talk floating point, real, and complex or byte. And so you can modify the kind of I/O on a block. There are also type converter blocks available. For example, the complex to float block has one blue complex input and it puts out two orange outputs. One is the real or the in-phase component, and the other is the quadrature or the imaginary component. So this is a diagram, and you can see I've got a multiply here without any wires hooked up, and it has blue inputs and outputs. Those are complex. And the real one on the bottom there is a multiply, and they're orange, and so those are real. So let's now talk a little bit about complex versus real. A real signal contains mirrored positive and negative frequency components. We just saw those on the previous flow graphs where we saw the negative frequencies. A complex signal allows differentiating the positive signals from the negative signals. So complex negative and positive signals can be different. And if you are interested in doing single sideband processing, you care a whole lot about that. It's possible to eliminate, for example, the negative frequency component. And there are some blocks in GNU Radio that will let you start with a real and convert it to a complex and then null out the negative components. Or you can null out the positive components if you wish. You'll find in GNU Radio that almost all radio processing blocks use complex signals because really you're interested in just a single range of frequencies and not having them double sideband mirrored. If you're interested in complex versus real, there's more details in the appendix that go into a little bit of the math behind that. So a multiplier, just multiplying the first input on a sample by sample basis with the second input is actually a mixer, and we showed that previously. Using complex numbers does not produce a sum and difference frequency like it did with real numbers. It only produces the sum frequency. And the nice thing about that is a complex multiply can produce a frequency shifter rather than getting all of these undesired sum and difference components. When you use complex numbers, it allows you essentially to put a tuning knob on signal and shift it up in frequency or shift it down in frequency. So if you wanted to shift a signal down in frequency, you would multiply a wideband signal with a negative frequency carrier. And those oscillators on the previous chart, you can actually enter in a negative number in the frequency, and that source will produce a negative frequency, and that will let you shift down. So it's an ideal way to take something at a high frequency and shift it down to a lower frequency. So you can enter the frequency as a negative number, or there's a mathematical operation called complex conjugate, and that will invert the frequency sign. So if you have a positive complex signal and you run it through the complex conjugate block, it suddenly becomes the negative frequency of that signal. And if you go through the math of signals, you'll see that it's a real easy thing to do. So let's go now to a second demo. And the second demo is, let's go find demo 2 here. And here we see that same flow graph that we had before, but all the blocks are blue rather than orange. And so these are blocks that work on complex signals. And if we go to the signal source here, you'll notice the type here is complex. And I could select float, for example, and it will turn orange. But then you'll notice my interconnecting arrow is red because we've got a mismatch in signal types. So let's go back and fix that and make it complex. And then, oh, okay, the flow graph is happy again. So now what happens when we run this flow graph? If we run it, we'll see now that we have just the single frequency at +1 kilohertz. Let's zoom back out. And you'll notice that there's no signal at negative 1 kilohertz at all, because the complex number allows us to represent a single-sided spectrum. Or we could have a different carrier at -2 kilohertz if we wanted to. But complex numbers inherently let us differentiate negative from positive frequencies. So let's now go look at demo 2B. And this is very much like the one we saw with real numbers. And remember, we got lots of products on the spectrum analyzer when we ran that one with real numbers. Let's run this with complex numbers. And here we see the two carriers, 1 kilohertz. Let's zoom in on that a little bit. 1 kilohertz here mixed with 700 hertz. And because these are complex signals, we only get the sum frequency up here at 1700 hertz. We don't get the difference frequency down here at 300. So in general, you'll find with radios that you want to use complex numbers, because then you can process signals and not get all of these weird components that you may not want. So each block in the flow graph has to know about the sample rate of the samples coming in. In all the blocks so far, we've used the GNU Radio default SAMP underscore rate, which it sets by default at 32 kilosamples per second. And so at 32K samples per second, we're limited to a frequency range of minus 16 kilohertz to plus 16 kilohertz. So a 32 kilohertz spectral width, but no frequencies any higher than 16 kilohertz. Some blocks can change the sample rate. And one of those blocks is called decimation. And what that block does is that it first low pass filters the signal, and then it keeps 1 out of every n samples. So for example, you may have a radio that wants to be clocked at 1 million samples per second on the output rate. Perhaps that's the hardware of the radio and it can't do anything else. Well, 1 million samples per second may make your poor computer huff and puff and work pretty hard. And it may be that you're really only interested in listening to audio. And so you can't hear by ear anything higher than about 8 or 10 kilohertz. And so you may want to decimate that down to a lower sample rate. And so if you decimated by 10, then the output sample rate would be 100 kilosamples per second with no frequency usable above plus 50 or below minus 50 kilohertz. There's an equivalent block called interpolation where you can speed things up. You can insert n zeros between each sample, then low pass filter. For example, that same radio might have a transmitter that has to be clocked at a minimum of 1 million samples per second, but you just want to feed it something from your sound card. For example, a microphone connected to your sound card. So you'd have to interpolate up the sample rate and then low pass filter it. So there's something called the Nyquist bandwidth rule, which says there's only good spectrum up to the half of the sample rate. As I like to say, it's not only a good idea, it's the law. So you have to keep track of sample rates in your flow graph. GNU Radio creates one default variable sample rate, but you can define a whole bunch of different variables if you want. And you might have one that's a receiver sample rate and a different one that's transmitter sample rate and a different one that's processing sample rate. And by controlling the decimation and interpolation ratios, you can make them all work together. Some GNU Radio blocks, for example, the low pass filter, can do both filtering and decimation in one block. And we'll see an example of that in a later flow graph. Very handy. A tip, if, for example, you're receiving, reduce the sample rate close to the receiver in order to decrease the processor workload. It doesn't make any sense, for example, to have an audio processing chain where the squelch and the audio gain are all running at 1 million samples per second when there's no audio components that you care about higher than maybe 8 kilohertz. And so you can decimate close to the receiver and make your CPU breathe a little easier. More details in the appendix if you're interested. So there's a couple of key modules in GNU Radio. There's actually hundreds and hundreds, but the ones you'll use all the time are sine wave. There's a noise source, a broadband noise source tends to be very handy for things. There's a constant where you can just stream in a constant number. You can stream in nulls, which is a constant of value 0. You've already seen the multiplier. There's an adder. There's all kinds of format converters. You've seen the spectrum analyzer. There's also an oscilloscope, waterfall, whole tons of things. I'd encourage you to install GNU Radio and play with all the blocks. The cost is nothing except your time. The others, there's filters, there's general types, there's low pass, band pass, high pass filters that are all pre-made for you. There's a whole bunch of different filter shapes and types available. So you don't even have to design the filters. If you want a custom filter, that's supported as well. And there is, in fact, a filter designer module within GNU Radio Companion. And you can go design custom filters if you'd like, and it will produce all of the information necessary for you to import that custom filter into GNU Radio, and you don't have to write any software. Again, there's more details in the appendix for that. So let's look at some other things GNU Radio can do. For example, it can make test equipment. And I'm going to give you something that's really useful, at least I found useful. And that was, I had a receiver and I wanted to measure the noise figure of the receiver. Now, normally measuring noise figure is a fairly complicated task, but we can do it in GNU Radio. And what we do is use what's called the Y factor method. So we have a receiver here in blue, and we have a calibrated broadband noise source. My noise source is a Zener diode and a battery and an RF choke and a capacitor. And it puts out 5 dB excess noise. That's 5 dB above the thermal noise. And what we do is we switch the receiver between a resistor, and typically that'll be 50 ohms. And that resistor puts out thermal noise at 273 degrees Celsius. And a broadband noise source. So when we flip the switch, the noise goes up by 5 dB. We flip it back down to the resistor, it goes down by 5 dB. And so if you plot the equation for noise figure, which is this equation here, we've plotted the increase in noise that we measure on the receiver on the x-axis. And then we solve for the noise figure, and that's the resultant value on the y-axis. So for example, if we turned this switch on and off and the noise went up and down 2 dB, and we're using this 5 dB excess noise ratio source, we would know that the noise figure of the receiver is about 7.5 dB. So by measuring the up and down in GNU Radio, we just hook up the receiver, we run the output broadband noise, even without any DSP, right into the spectrum analyzer, and we look at the level, and we flip that switch back and forth, we can actually measure the noise figure. So this is the resultant flow graph from GNU Radio. And in the blue, you can see the noise coming out of the receiver when that noise source is turned off. And the gold is the noise coming out when it's turned on. So I stored the gold using the max hold option. So this isn't really quite the average. It's slightly higher than the average, but it's close. So this is the spectrum going from minus 24 kilohertz to plus 24. The center frequency is 29.5 megahertz. So this is at the top of the 10-meter band. So I measured a Hermes SDR receiver that had in front of it the Alex filters. And these are filters that set the band that you're listening to, and has a bunch of relays for, do I want antenna number 1 or antenna number 2. I averaged the spectrum, and I set the display for 2 dB per division. And you see the difference here is just a little bit less than 2 dB. And so that says that the noise figure of the Hermes receiver with an Alex in front of it is about 8 dB. So we're able to characterize the receiver. We've done all of this with just an SDR receiver, a simple noise source, which only costs a couple dollars to make, and we just wired it all up in GNU Radio. So there's all kinds of things you can do with the virtual blocks and the radios. It kind of is up to your imagination, but you have a pretty powerful piece of test equipment without really spending much money. So let's look at a third demo. It wouldn't be GNU Radio if we didn't have a radio. So I have hooked up to my local area network the same Hermes and the Alex. I'm going to turn on the power supply, and there's a fan in it. I built a Hermes module and an Alex and 100-watt Union PA, and I put it in a Cooler Master computer chassis and feed 12 volts to it. So it's a 160 meter to 6 meter 100-watt transmitter receiver combination. So it's a transceiver on a box. So this receiver is going to be based on a homodyne down conversion receiver. And what homodyne is that the hardware that does that first down conversion, that generates an IQ local oscillator and then mixes it down to 0 in the radio hardware, is doing that inside an FPGA in the radio. And the reason is the A to D converter in Hermes is clocked at 122 million samples per second, megasamples per second. And so that down conversion process is having to do a complex multiply once every 8 nanoseconds. And really there's difficult for a computer to keep up with that. So instead we do that in hardware in the first stage. And so we'll implement an IQ local oscillator right on the same frequency we want to listen to. And that will slide by multiplying and frequency shifting down to 0, the signal we want to listen to, and it'll come out of the radio as a complex number from minus some number of kilohertz to plus some number of kilohertz. Then our GNU radio flow graph will go zoom into that baseband signal, which is just a collection of samples being streamed from the radio. In this case, we'll use the Weaver method to select one sideband. We'll do filtering and automatic gain control on it, and then we'll send it out to a sound card. Now, I have a sound card on the same computer, and I'm running this GNU radio on the same computer that I'm doing Zoom. Zoom, however, will not let me run the output into the input. What Zoom does is it squelches your audio when you talk so that you don't get feedback. So I have speakers plugged into the sound card on the computer, and I'm going to take my headset off and hold the microphone up to the speaker so that you can hear it come through the Zoom audio. So let's go ahead and bring up the third graph and close these two. And so here is the flow graph. Now we have is the receiver Hermes, and Hermes is the one of the Anon radios, which is also OpenHPSDR, which is Hermes. Pavel Denin wrote an OpenHPSDR for Red Pitaya. And so if you have a Red Pitaya and you load his code into the Red Pitaya, it will talk OpenHPSDR on the output, and then you can use this module to stream samples into your flow graph. I wrote this module, this Hermes module, about 8 years ago, and have been updating it, and it's been used in a lot of science and a lot of ham experiments. So we'll look at the output of that on a spectrum analyzer. And so our sample rate here, you'll notice that I've defined the sample rate variable. I've changed the GNU radio default to 384,000 samples per second. That sample rate that's supported by the Hermes module. So we're going to clock it out at 384K. I'm going to run it through a low pass filter, and that low pass filter cutoff frequency will be 2.5 kilohertz, or minus 2.5K to plus 2.5. But we're going to shift that around a little bit so we actually hear 5 kilohertz of audio coming out. I'll then multiply it with a signal source to shift this thing going from minus 2.5 to plus 2.5 up by 2.5 kilohertz. So the audio coming out of the mixer here now goes from 0 to 5 kilohertz. We'll run that into another low pass filter, into an automatic gain control, and then into a volume control. And then I'll convert that complex to a floating point number and run the floating point output to the audio sound card in the same computer. And here I've told it that I want it to use the sys default card, which is the sound card, rather than some other audio output. So now if we go ahead and run this, Okay, I'm going to have to do one thing. There's a bug in the Alex hardware where until you actually cause some relay to flip, it doesn't actually select anything. So we're going to manually go in and tell it that we want to change which receive relay we're using. Run the photograph and stop it, and then go back, and then it will select the proper relay. That's a little bug in that particular module. So we're listening to the AM broadcast band here. And let me go move the Zoom panel here out of the way. So let's turn on a grid. Now we have a grid of frequencies here. The blue is the wideband output of the receiver, and the red is the output of that little low pass filter in the middle. So let's take the tuning knob here, and this just programs the frequency of that mixer, and we'll go slide this down, and we'll turn up the volume a little bit. And I'm going to take my headset off and hold the mic up to the speaker.
He gets it going. You know, they're really tough, and he got it going at our place the first half, and fortunately we.
So you can see that the speaker is outputting AM radio, which may not be too useful. There's a bandwidth knob here. I wired the bandwidth control to one of the filters. And you can notice that the spectrum widens out as I open up the bandwidth. If we can also move the tune control too narrow, and if we listen to it now, and you can tell that the frequency response is now very restricted. So that's just an example of a radio that's got an actual single sideband, single signal receiver on it, and allows you to adjust the filter bandwidth, allows you to change the volume. Now, if you look at the console window down here, let me highlight this. One of the things that I tried to do in driving this is actually keep track of the packets. So it'll tell you that the radio it found on Ethernet interface ENP3S0, and in Linux, that's normally the first Ethernet interface on the Linux box. So this computer I'm doing the presentation on is talking over the LAN to the Ethernet connector on Hermes. And it tells you the IP address of your local machine, your local machine's MAC address. The target is the Hermes and its MAC address and its IP. And notice when I stopped the flow graph, it tells me about the packets. It said that it lost no received packets. It received a total of 306,000 packets. It lost no transmit packets, and there were none corrupted. So essentially, it had an error-free connection to that radio over the Ethernet connection. You'll notice that Hermes is actually a transceiver. It will transmit and receive. I put in a constant source of zeros. That's a null source or a constant zeros. And when you feed all zeros into a transmitter, the transmitter puts out no RF power. So in this flow graph, I'm not using the transmitter, I'm just using the receiver. One of the interesting things on Hermes is that it can support up to 7 channels. And so if I go tell the module to implement 7 receivers here, you'll notice we now have 7 completely independent outputs. We can program the frequencies of those outputs completely independently of one another and stream them separately through the flow graph. And so, in fact, if we wanted to, we could listen to WWV on all channels all at the same time if we could figure out how to separate out all the audio, or we could run each of the channels into a different wave file on a different file. So we could do multi-channel audio recording. We have a lot of options that we could do there. It's going to ask me if I want to save, and I'm going to close without saving. So there's a lot of good references here. GNU Radio has a wiki. It's maintained. And Barry Dugan does a great job in updating it. A lot of other folks update it. Again, these references are in the slide deck. OpenHPSDR.org has the standards for the OpenHPSDR radio. The Red Pitaya website will give you links to Pavel Demon's Red Pitaya open source firmware. You need my driver to talk to it. My webpage, I've done some science experiments. I did a bunch of experiments where I was able to measure the height of the F layer of the ionosphere and measure its vertical velocity using the equipment that we just demonstrated, the Hermes and Alex. I was able to send echoes off. I could hear echoes, double transit echoes, go up to the ionosphere, come down to ground, go back up to the ionosphere, come back down to ground. My GitHub page has the drivers for OpenHPSDR. John Petrich's has a good web page. John's done a lot of work with microwave DSP. And so at the MUD conference last year, we actually demoed 2.4 gigahertz microwave radios using an Atom Pluto and GNU Radio. So we were able to carry on a single sideband QSO at the conference on 2.4 gigs. And then the ARRL Tapper Digital Communications Conference. And if you're interested in software-defined radio, GNU Radio, Tangerine SDR, and more, it's a great way place to go. And then there's a bunch of slides in the appendix. We won't go over those today, but if you have more interest in certain areas, take a look at the appendix and it may help you out. So with that, probably time for questions and answers.
All right, we have now unmuted everybody. So, or actually you can unmute yourself or raise your, okay. Jerry has his hand up, and go ahead, Jerry.
Hello,
Jeremy, I'm
thanks
sorry.
for that presentation there, Tom. That was really super. You mentioned the Hermes. You also know the number of dollar signs that thing gets?
Well, Hermes, the Tapper version was a one-time production. And they were, I think when they produced them, they were around $895 or so.
$895.
Yeah. There is a
That's up there.
there's a Hermes Lite module that is, I think, around $200. I don't know if it has a transmitter. It might, but the Hermes module is pretty high performance. It's got pretty good specs. You can find literally dozens or hundreds of SDR radios that will transmit and receive at all different kinds of price points.
I was thinking spectrum analyzer, so no need to transmit. So I'm wondering, like, what's the maximum bandwidth signal that it can accept? You know, like, can it do a Wi-Fi at 20 megahertz of bandwidth?
Yes, it can. The fastest I've run it on this computer is 56 megasamples per second. So I was able to get a little over 100 megahertz of spectrum. However, the graphics, I used a special driver that uses the NVIDIA graphics card in the computer to actually do the spectrum processing. And then I've got a real fast color spectrum display. And in real time, you can see Wi-Fi bursts come and go in the millisecond range. If you don't use that driver, you can really only kind of see the average Wi-Fi spectrum, but you can in fact see the Wi-Fi spectrum and tune back and forth.
Spectrum, okay.
Yeah.
And as far as maximum frequency for a $200 type of SDR?
I don't know. You'll have to look at what's available. It changes pretty much on a weekly basis.
And where do you go shopping?
A couple of units, the Analog Devices Pluto is one that a lot of folks have used because it's inexpensive and it goes up into the microwave range. I have an Edis transmitter receiver unit that goes from 70 megahertz up to 6 gigahertz.
Oh,
And
wow.
so it will, and so
And how-
I've received up at 6 gigs on it.
And how much did
it-
that cost?
That was around $800 or $900.
Okay, it's up there. All right.
Yeah.
Great.
And the Atom Pluto, I think, goes up to at least the 2 gigahertz Wi-Fi band. It may go up to 5 gigs. So there's a huge range of radios, prices, features. You can get an RTL SDR dongle for less than $20. It's
Yeah.
receive only.
Yeah,
And
that one
they-
seems to have a very low, very small number of bits for the analog to digital converter, so it doesn't have much of a dynamic range.
Yeah,
You know
you have to be careful. Its sensitivity and its dynamic range are poor, but for $20, you get what you pay for. But
Yeah,
There it
folks are using those to listen to ADS-B, the aircraft telemetry beacons on 1090 megahertz, and they work
Yeah.
perfectly well. I've used them for FM broadcast band receivers.
yeah,
You
that
can
works good there.
see digital TV carriers, and you can see the broadband digital spectrum, and you can usually see the analog carrier. So there's better versions of those available, and I think Daryl's holding up one of the better ones of those that have a little bit
Yes,
better performance.
It's
Oh,
version
okay.
3.
Yeah,
And you can modify it for HF too. You got to go in there and do some, I think, solder some jumpers, but you can change it to work on HF as well.
Okay. Fabulous. Thank you, Daryl.
Okay,
And
Mike,
thank you for your time.
Mikey, you got your hand up, so go ahead.
Yeah, two couple of things. One is I went to the new radio website and I saw an SDR RTL listed quite a few different ways. Things that you could do with this software.
yeah. Let me go back to references here, and there is an RTL SDR website, and it generally is connected to a large number of SDR receivers around the planet. And you can listen to the receiver at that location just using a web browser. And so RTL SDR, I don't have it on my list of links here. I've had it in the past. It will allow you to go hear yourself. You can find a receiver in Europe and dial in a channel you want to listen to. And then if you're being heard in Europe, you could actually hear yourself on the radio. So there's a lot of things. John Petrich may have that on his. It's useful. It's not really GNU Radio. It's more just RTL SDR.
Yeah, I wanted to mention that based on what Daryl said, my SDR, it's a RTL, true RTL SDR. And anyway, you can switch frequency bands from high to low and go down to something around 20 megahertz on it, where normally it's up around 100 or whatever. But,
It takes a hardware modification.
no, you don't have to. Software will do the switch for you if you have the right version of dongle.
Oh, okay. I'll have to check that out. I was not aware of that. The instructions I saw where you had to do a little tiny hardware modification. It wasn't difficult. I think it was undoing a jumper or two, but that's very interesting. I'll have to check that out.
That was for the earlier version of the dongle. The later version, they fixed it so you can just do the switch in the software.
Yeah,
What version did they make that?
Huh?
What version did they? I got a version 3. Can you do the software switch with a version 3?
I think so, because I think mine's a version 3.
Okay. Okay, go ahead, Tom. I'm sorry.
Yeah, a lot of the inexpensive units rely on chips that really aren't intended to go below about 100 megahertz. And so there's a lot of workarounds if you want to listen to HF on these. One of them uses a crystal to upconvert HF into something that the inexpensive RTL dongles can hear. Others try to bypass the filters on the front end. But again, if you have a low performance device, you may not have good enough dynamic range for HF. So it's something that you can play with. And if you get serious, you may want to look at something with more performance. And if you don't, well, then they're pretty good to play with and fairly inexpensive.
Yeah, for $20, I'm perfectly happy with mine.
I was wondering if the RTL SDR had good dynamic range. That was I'm thinking, well, that cheap, maybe it's not so hot, but I guess I'll have to find out.
Right.
All right. Do we have any other questions? We're at 5 minutes till. So any other questions? If not, Tom, thank you very much. Awesome program. And everybody can do the appropriate reactions, I suppose, on there because we can't hear each other clap. So we only hear one. So there you go. And we got quite a few up there, looks like now. Everybody's so. Tom, thank you very much. You may go or stay with us. We just got one more presentation. Gordon is coming back. He was on this morning, and we'll give everybody about a minute or two break. Our last program of the day will be protocol development for JS8 for emergency nets. Sounds interesting. That's going to be, so I know Gordon's going to get ready, and we're going to end the YouTube stream if no more questions. And